Okay, welcome back everybody. So, last time the most important things that we showed were the following. So first, there was the Cauchy integral formula, okay, which, just to remind you, meant that if you had an analytic function f that was analytic everywhere inside and on a simple closed contour C, it's positively oriented, then at any interior point, I can compute the value of the function in terms of this contour integral of the function f over z minus point z naught, and I'm multiplying by this constant 1 over 2 pi I. So what is what is nice about this? Another way of viewing this, of course, is that this actually provides us with a pretty clever way of computing some of these contour integrals. So rewriting this formula slightly, this just moving the constant over, allows me to, if just plugging in, a complex number into my function, this on the right hand side I can compute pretty easily. So if I can write a contour integral in this form for such an analytic function, then I can use this Cauchy integral formula to compute this contour integral in this way really quickly without actually having to do any of those integration techniques I was doing before. So this is really nice. Now, one of the things that this said, as I mentioned last time, is that if you had an analytic function on a curve and everywhere inside it, then the values of f inside the curve are completely determined by the values of f on the curve. Okay, so this is something that is kind of a thing that characterizes how analytic functions behave in the complex plane. So this is something that is definitely special about complex analysis. Okay, and of course this formula could be extended to be applied not just to f itself, but to derivatives of f. And so this extended Cauchy integral formula says that if f is analytic on a simple closed contour C and at all points inside it, and if z naught's an interior point to this simple closed contour, then actually this now I'm rewriting it in the last way, where this contour integral of f over this power of z minus z naught, so it's over the n plus first power of z minus z naught, is actually 2 pi I over n factorial times the nth derivative of f evaluated at that point. Okay, or writing it like the original Cauchy integral formula was written, the nth derivative, okay, the nth derivative of f is at evaluated as z naught is n factorial over 2 pi I times this contour integral. And you can notice that if n is equal to 0, then the 0th derivative of f, that's taken to just be the function itself. So this is, if n is equal to 0, this is actually just the Cauchy integral formula. Okay, because 0 factorial is defined to be 1, so this would be the value of f at z naught is 1 over 2 pi I times the integral of f over z minus z naught to the first, right? Okay, so both of these taken together, or if you like to view the normal Cauchy integral formula sitting inside this, this is extremely important because this is going to allow us to show this fact that I've mentioned almost since the first week of class, that is one of the key things that differentiates, pun intended, between complex analysis and real analysis. Okay, and this is namely that the derivative of an analytic function is analytic. Okay. All right. And so that is actually going to be the first consequence that I talk about and that I actually care about here. Okay. And so let's get to discussing that. So now we wish to derive many nice facts from the Cauchy integral formula. So we wish to derive many nice facts from the Cauchy integral formula. And when I say the Cauchy integral formula, I may be talking about its extension, but I don't really distinguish between them. And so I just consider all of these things to be applications of the Cauchy integral formula. Okay. So the first one, that is this fact that I have mentioned, like I said, since the first week of class. If f is analytic at a given point, then its derivative of all orders, then its derivatives of all orders are analytic at that point too. Okay, and then just using the definition of analytic, what this means is that if I have a function that's analytic on some domain, then its derivative, f prime, is analytic on that domain. And the derivative of f prime, of course, then applying that part of the theorem to itself, the derivative of f prime, which is f double prime, is also analytic at every point in the domain. Okay, and continuously applying it like that in that inductive fashion, this means that every single derivative of any order is analytic on that domain. Okay. All right, so this is the fact that I mentioned earlier that says that if you have one derivative, right, then you have them all. Okay, which is a very special thing that's going on here. Okay. And so how do I prove this? Okay, so assume f is analytic at some point, we'll say z0. By definition, what does this mean? So by definition, remember, being analytic at a point means that you have a derivative in some window, right, in some neighborhood of that point. And so what that means is that, by definition, there must exist a neighborhood of z0 that we'll call, say, the window. It's the disk, the set of all z, such that z minus, or the modulus of z minus z0 is strictly less than epsilon. So there must exist a neighborhood of z0 throughout which f is analytic, or on which f is analytic. Okay. Okay. So, what's the idea here? Well, let's draw a picture. Here's my point, okay, of some domain in the complex plane. Okay, maybe my domain looks like this, right? I don't really care, I didn't mention it. Okay, maybe my domain looks like that. Okay, well, the idea here is that there's some neighborhood at this point, and we'll say this neighborhood has radius epsilon. So some neighborhood at this point, maybe I'll do it in a different color. Okay, on which f has to be analytic. Okay. Well, if here's my radius and this is epsilon, okay, well, what this means then is that if I want to try to apply the Cauchy integral formula, of course, or its extension, requires that I'm doing this over some simple closed contour, and the simple closed contour is such that f is analytic on the contour and at all points inside of it. Then I'm looking for a simple closed contour C on which to apply the extended Cauchy integral formula. So then I want to choose simple closed contour C that's entirely inside this thing here, right, this neighborhood. Well, that's easy to do, right? Like this one will work. And what is that one? Thus, C taken to be the simple closed contour given by the circle, which is modulus of z minus z naught is equal to, say, epsilon over 2. That's guaranteed to be inside that neighborhood. Right? It lies entirely inside this neighborhood. It lies entirely inside this neighborhood, but f is analytic throughout that neighborhood. Thus, f is analytic on C and at all points inside C. And at all points interior to C. So we can apply Cauchy integral formula. We can apply Cauchy integral formula. I'm not going to say it. I'll just put ... there since I ran out of room. Okay. So let's apply Cauchy integral formula. Specifically, I want to apply this extended formula. Okay, and I'm going to apply it, say, to its second derivative. Okay, so by extended Cauchy integral formula, we know, for instance, that f double prime of z is equal to 1 over pi I times the integral of c naught, or times the integral over, I'm calling it c, times the integral over this c of f of s ds over s minus z cubed, okay, for every z interior to C, right? Okay. But then what have we shown? Well, what that means is that f double prime z exists, right, for all z in the neighborhood given by the interior C, right? Which is exactly the set of all z such that the modulus is z minus z naught strictly less than epsilon over 2. We've shown that this thing exists on some neighborhood of z naught, but if f double prime exists at some neighborhood of z naught, this means that f prime of z is analytic, right? F prime is analytic at z naught. So what have I shown? I've shown that if we start out, right, with the assumption that f is analytic at z naught, then we get that f prime is analytic at z naught. Following the identical argument, right, just literally substituting for f prime, we get that f double prime is analytic at z naught. And then substituting that, we get that f triple prime is analytic at z naught. Thus, continuing on, right, all derivatives of f are analytic at z naught. And that does it. So we started out with a completely arbitrary point. If it was analytic at that point, then its derivatives of all orders are analytic at that point. See, so that wasn't even, that theorem wasn't even very involved. It literally just fell out of the Cauchy integral formula. Okay. All right. So this is an extremely nice fact, and as my point for mentioning this earlier, my point for mentioning this earlier when I first introduced this idea before I had actually talked about any of these things, was to illustrate exactly where we're going and exactly how different this is from the real case, right? Where there is no analogous statement that's even close to being true about real valued functions like this. Okay. So, a quick consequence of this. Okay, and this was something that you might have predicted if you noticed this while we were talking about harmonic functions earlier in the course. So this is a fact that's true about harmonic functions, and like I said, you may have noticed that we actually have this consequence from our dealing with harmonic functions earlier. But let's rewrite f as u plus iv, okay, in the usual way. Okay, so what does this mean? Well, since or if f is analytic at z, then f prime is differentiable at z, right? Thus f prime is continuous at z. Right? Differentiability implies continuity. But of course, f prime can be written as u sub x plus I v sub x, or it could be written as v sub y minus I u sub y. So if f prime is continuous at z, the first order partials are continuous at z. So first order partials are continuous at z. But we can keep going here, right? So let's continue. So continuing, f double prime exists at z. Thus, f double prime is continuous. Or I should say f double prime, I could say f double prime is actually analytic from the function. Okay, so it is analytic more than just it exists. F double prime is analytic at z, thus it is continuous at z. Thus, since f double prime can be written as u sub xx plus I times v sub xx, which can also be written as taking the x partial now of the second equation that I wrote before, v sub yx minus I u sub yx. Okay. Then the second order partials, since f double prime is continuous, these must all be continuous as well. Okay. Now you might complain and say that we didn't get all of them here, right? But actually we did, because these commute. Okay. And so, thus we have shown the following corollary of that theorem, which is the thing that, like I said, we actually notice when we're first dealing with harmonic functions, which is if you have an analytic function at a point, then the component functions have continuous partial derivatives of all orders. So if f of z is equal to u of xy plus I v of xy, okay, written in the usual way, if this is analytic at a point z, which is x plus iy, or xy, right, written as an ordered pair, then the component functions u and v have continuous partial derivatives of all orders at that point. Have continuous partial derivatives of all orders at that point. Okay. All right. So this is a really nice fact that corresponds to that previous nice fact about the existence of derivative of function guarantees the existence of higher order derivatives of the function at the same point. Okay. So this is a pretty amazing thing. Okay. So next we have another named theorem. This is called Marrera's theorem. So this is going to provide a converse direction with certain assumptions. So this is known as Marrera's theorem. So what's Marrera's theorem say? Well, let f be continuous on a domain D. Okay, if the contour integral of f along every closed contour C and D is 0. So if this contour integral is 0 for every closed contour C and D, then f is analytic on D. Okay. Okay. Note, before I move on here, right, the relationship of this to some of the stuff we did surrounding Cauchy-Gauss. Okay. So note, if D is simply connected, so this is simply connected, then this is a converse to our Cauchy-Gauss on simply connected domain theorem. I don't think we had a name for it. I think I just said Cauchy-Gauss on simply connected domains, right? So this is a converse to Cauchy-Gauss. Cauchy-Gauss said the opposite. It was that if you had a function that was analytic on a simply connected domain, D, then this contour integral was always 0. So this is, like I said, in the case that D is simply connected, this is actually a converse to that fact. Okay, so this relates a function that's continuous on some domain, satisfying this fact that all these contour integrals along every closed contour is 0 tells you something about the analyticity on the of the function on the domain in question. Okay. So this is actually a pretty easy proof. So proof of Marera's theorem. So how do I do this? If we assume this condition, that this is 0 for all closed contour C, then by that equivalent condition on my big theorem, then by my Ftcc, fundamental theorem of complex calculus, right, that I had before involving antiderivatives, this means that f of z has an antiderivative, big F, okay, throughout D. But what's an antiderivative big F of z throughout D? I.e., f of z is analytic, and if I take the derivative of big F of z, I get little f of z, right, for all z in D. Okay. But then I have an analytic function by my previous theorem. Its derivatives of all orders are analytic on D, but in particular, f prime of z is analytic, so its first derivative is analytic on D, but f prime of z is equal to f of z on D. So since f prime is analytic, f is analytic. But that's exactly what I was going to show, right? And that's it. Okay. So that's the deal. Okay. One more named theorem in this section, and then we are going to use all of these applications to do even more applications. Okay. So the next named theorem is called Cauchy's inequality. Okay. So this is Cauchy's inequality. And this has a variety of applications. Okay. And so the assumptions here are as follows. So suppose that a function f is analytic. So suppose a function f is analytic inside and on a positively oriented circle we'll call C sub r here, okay, centered at z0, with radius r. Okay. If big M sub r denotes the maximum value of the modulus of f of z on C sub r. First of all, why would this exist? Well, F's analytic, okay, inside and on a positively oriented circle, C sub r, okay. That means this modulus is continuous, right? We don't need it to be analytic. We need it to be continuous here. So we have a continuous function on a circle in the plane. Circle in the plane is a closed and bounded set. I have a continuous function on a closed and bounded set. So by our version of the max-min theorem, this thing has a maximum. It actually attains that maximum on that set too. Okay. So this thing is going to exist. So if m sub r denotes the max value of modulus of f of z on the circle, then the modulus of the nth derivative of f at z naught is less than or equal to n factorial times big M sub r over big R to the n. And this is true for n a natural number 1, 2, 3, 4, and so on. Okay. So this is true for all n. Okay. So the idea here is as follows. All right, so here's my point z naught. Say that so this forms my center of the curve in question. Here's curve in question, which is circle of radius r centered at z naught. So here is my radius r centered at z naught. So the idea is there is a bound on the nth derivatives that depends on n, okay, but then that's multiplied by this constant that doesn't actually depend on n. This is just coming directly from the max value of the modulus of my function on this circle, okay, around that circle. Okay, and yeah, it's positively oriented. Okay, all right. Now, how do I prove this? Proof is actually pretty easy. It is immediately true from our earlier work on bounding these things, bounding these contour integrals, or bounding the modulus of these contour integrals. So just apply this directly to extended Cauchy integral formula. So by extended Cauchy integral formula, we know that at z naught, the nth derivative of f at z naught can be computed by this integral. It's n factorial over 2 pi I times this contour integral over c sub r of f of z dz over z minus z naught to the m plus 1, right? And that's true for all n, okay? And so, what does this tell me? Well, if I slap bounds on this, so slapping bounds on this, I get the modulus of the nth derivative at z naught has to be less than or equal to n factorial over, I'm taking the modulus of everything, modulus of I is 1. This is 2 pi times the maximum of the modulus of f of z, right, is, I've already defined that as m sub r, so this is m sub r, that's the bound, okay, on on the modulus of f of z, okay, over this thing, right, on this curve, is just r to the m plus 1, okay, times, I'm doing the contour integral along this curve, right, so what do I get from this? This is 2 pi r, right? Okay, 2 pi r is the circumference of this circle, right? This is what pops out of there. Okay, and so this is exactly this form taken by this boxed inequality. Okay, and so that's that. Okay, so that's Cauchy's inequality. Okay, so we're actually going to use Cauchy's inequality later to show some more of these named theorems that we're going to go after. So the first one, we're going to immediately apply Cauchy's inequality. The first one is also something I've mentioned before, namely this is Louisville's theorem. Okay, so more applications. Of these facts. So first, we have a theorem that I've already stated to you before, but now we're going to prove it. Louisville's theorem. What is this? If a function f is entire, that is analytic on the entire complex plane, and bounded, if it's entire and bounded in the complex plane, then it is constant. Throughout the entire plane. This is pretty amazing, okay? If it's entire, that is analytic on the whole plane, and bounded in the complex plane, it actually has to be constant. Okay. Why is this amazing? It's so radically different from what happens with real valued functions. Look at sine x or cosine x, right? Sine x is taken as one of the premier examples of a function that is differentiable everywhere. It's analytic in the real sense, okay, which, as I've said, means that it has a power series expansion. You know its power series, it's just the Taylor series of sine. So sine x has a power series representation at all points. It is about as nice as a function as you can imagine. It's bounded, right? One of the key facts about sine x is it's bounded between 1 and minus 1 for all values of x, right? So it is bounded and analytic. It is most certainly not constant, right? Sine x is definitely not constant. Okay, but what this says then is that that sort of thing can't happen for complex valued functions. For complex valued functions, if you are analytic everywhere, okay, so if you're analytic on the entire complex plane, that's important. Okay, so it's not just everywhere on some domain. So if you're analytic on the entire complex plane, okay, and you're bounded on the entire complex plane, then you actually have to be a constant function. Right? So how does this work? Okay, well, suppose f is entire and bounded. Okay. All right. Then I can apply Cauchy's inequality with any z naught and r as my choice. Right? So, when n is equal to 1 in Cauchy's inequality, let's bring that back for 1 second. Right, here's Cauchy's inequality. So if I take n to be 1 here, this is going to provide me with a bound on the first derivative at that point. Then the modulus of f prime at z naught is less than or equal to m sub r over r. Right. Now, f bounded implies there exists big M such that the modulus of f of z is less than or equal to big M for all z, right, in the entire complex plane. Okay. Now, and since this M sub r is always less than or equal to M, why? Well, if this is going to be true, then this maximum value of my modulus applied to some circle, right? Well, as I'm changing the radius r, that is going to change, but it can't be larger than this maximum that we're applying to the function on the entire complex plane, right? Because this has to be true everywhere, whereas the inequality, this thing only need be satisfied on a circle, right? So this is our maximum value on the circle, say C sub r. This has to be true everywhere. Okay, and so this is true, i.e. another way of incorporating this, knowing this, is that my bound on f prime must actually be m over r. Oh, what is the point here? Right? Why did we want this instead of this? We wanted to remove the dependence of this thing on r. Note, this numerator does not depend on r. Right? This bound is the thing that must be true on the entire complex plane, i.e. it doesn't depend on the circle, right? Okay. That's important because what we want to do here is we want to take r to be whatever, right? Arbitrarily large. Okay. So we want r to be large. So this has to hold for arbitrarily large r here, right? That's what I said originally. I can apply Cauchy's inequality with any z naught in r, right? And so this r can be as big as I want it to be. Okay. So take r to be arbitrarily large. If I take r to be arbitrarily large, then this bound f prime, or on the modulus of f prime 0 naught, if I take r to be arbitrarily large, then this thing goes to 0, right? So the only way this could be satisfied for any value of r here is if this thing is actually equal to 0. So f prime of z naught is actually equal to 0 here. Okay. But, as I said, the beginning of this proof, I can apply Cauchy's inequality with any z0. So I use the fact that I could apply this with any r to say that, well, I can pick r as big as I want to, which means that this thing has to go to 0. So then I get that f prime of z0 is equal to 0. But this then must be true at any z0. Okay, this is true for all z0 in C, i.e. f prime of z is equal to 0 for all z in the complex plane. But then this, we already know what this means. This is one of the first things we showed, right? Once we had talked about a complex derivative. This is one of the first theorems we proved. This means that f is constant on C. And that's it. So a bounded entire function is constant. Okay. This is a pretty amazing fact here. Okay. It's going to immediately lend itself to our use of proving another big named theorem that you know in some form. I'm going to state it in the following form, then I'm going to show you how it implies any other form of this thing that you have seen. This is the fundamental theorem of algebra. Okay, so we can use this to give an easy proof of the fundamental theorem of algebra. So we can use this for an easy proof of the fundamental theorem of algebra. Okay, so another big named theorem, fundamental theorem of algebra. What does the fundamental theorem of algebra say? It can be stated in many different ways. One, if you have more algebra knowledge, you could just say the complex numbers as a field are algebraically closed. Right? Well, that's not going to be how we say this. The way that we're going to state this is as follows. Any polynomial we'll write this as P of z is a0 plus a1z plus a2z squared and so on all the way up to a sub n z to the n. Okay, where we take the leading coefficient to not be 0, just so that when we see this written out, we can say its degree is n, right? So a sub n is just the largest coefficient, which is non-zero. Okay, so any polynomial of degree n greater than or equal to 1 has at least one zero. So it has at least one root, i.e. there exists at least one z0 such that P of z0 is equal to 0. Now we'll see in a second after I prove this why this is the same fundamental theorem of algebra you've seen in any other context. Maybe the most popular form of it is that when you have a polynomial written like this as a polynomial of a complex variable, you can fully factor it. Right? So a polynomial of a complex variable fully factors into linear factors. Okay? So there is no such thing as, say, an irreducible polynomial in this sense. So if you think of an irreducible polynomial as being a polynomial that you can't factor, Okay, and so for instance, there were polynomials you couldn't factor in the reals, right? So like x squared plus 1, right? You know what the roots of x squared plus 1 are. They're complex numbers. They're plus minus I, right? So that thing would not factor as a product of two degree 1 polynomials having real coefficients, because in order for that to factor, you would have to have complex coefficients, right? It'd be x plus I, x minus I, right? And that's not allowed. Those aren't allowed factors because that would require coefficients that are complex, not real numbers. Okay. So over the reals, you couldn't factor that polynomial fully, x squared plus 1. But over the complex numbers, you can absolutely factor z squared plus 1 fully. And it factors as z plus I, z minus I. Boom, right? That's it. You're done. Okay. All right. So any polynomial of degree greater than or equal to 1 has at least one zero, and I'm going to show you how that leads to that statement I just said, that any polynomial like this fully factors. Okay, so proof of fundamental theorem of algebra. So suppose not, i.e., suppose that this polynomial, p of z, is non-zero for all z. Right? So for all complex numbers, suppose that polynomial is non-zero. Well, then, f of z, which is defined to be 1 over that polynomial, since this thing is never 0, and it's a polynomial, this thing is analytic everywhere, right? This is analytic everywhere, i.e., it is entire. Okay. So if I consider the reciprocal of that polynomial, this thing is entire. So that's nice. Question is it bounded? Is it bounded? Well, if we define w, so if w is defined to be a naught over z, a naught over z to the n plus a sub 1 over z to the n minus 1, and so on, all the way up to a sub n minus 1 over z, right? Then we can rewrite our p of z as a sub n plus w times z to the n. Let's just check that this actually works. So here's some algebraic trickery here. So if this is my w, and I define, if I define w to be this thing, a sub n plus w would be this thing plus a sub n here. If I multiply that by z sub n, I would get a sub n times z sub n plus a sub n minus 1 times z to the n minus 1 plus a sub n minus 2 times z to the n minus 2, all the way down to a sub 1 times z and a naught times 1. Right? So this is just some algebraic trickery to do this. Okay. All right, now note also that for each term in w, okay, I can find a sufficiently large big R such that the modulus of each of these quotients is less than or equal to the modulus of a sub n over 2 to the n when z is exterior to a circle of radius r. Okay. Then I apply my generalized triangle inequality. Okay. By the generalized triangle inequality. Oh, I can actually do this in such a way that this is a strict inequality. So I can actually do this in such a way that this is true. Okay. And thus, I know that the modulus of w is strictly less than this modulus of a sub n over 2 times n, not 2 to the n. Sorry. I can actually get rid of the dependence on n in the denominator here. So this is strictly less than the modulus of a sub n over 2. Okay, whenever z is exterior to that circle of radius r. Okay. And so, what does this mean? Again, from triangle inequality, the modulus of a sub n plus w is greater than or equal to the modulus of the absolute value, or the absolute value of the modulus of a sub n minus the modulus of w. Sorry. But again, by this fact, this is strictly greater than the modulus of a sub n over 2. Again, whenever the modulus of z is greater than r. Okay. So what is the point here? Thus, if I look at the modulus of this p of z, right, which I have rewritten as a sub n plus w times z to the n. This is the modulus of a sub n plus w times the modulus of z to the n. Okay. But going back, I have this bound, right? So that this is, I'm a little bit off the screen here. So that this is strictly greater than modulus of a sub n over 2 times r to the n when modulus of z is strictly greater than r. Okay. But then if I look at the modulus of f of z, this is 1 over the modulus of p of z, which is strictly less than 2 over the modulus of a sub n times r to the n, right, whenever the modulus of z is greater than r. So it's bounded outside the circle. It's bounded inside the circle by the max-min theorem. Okay. So f is bounded outside the circle C sub r. Okay. It is bounded on and inside C sub r by Max-Min theorem, since it's, say, continuous there, right? That's all you need, because this is a closed disk. Okay. But what does this mean? F is bounded everywhere on C. So this was, we had to work kind of hard for this, but what was it that we were doing? Well, we showed immediately that this was entire by our assumption. So F is entire. We did a lot of work here to show that F is bounded everywhere on a complex plane. So it is bounded and entire. Thus, by Louisville's theorem, F is constant. But if F is constant, since this is just 1 over the polynomial, this implies that P of Z is constant. The P of Z is just a polynomial, right? It's not constant in general, right? Unless you are dealing specifically with a constant polynomial where all of the, a degree 0 polynomial, right? A polynomial cannot be constant if it has degree greater than 1. And that's exactly the case we're in, right? This is a contradiction. Okay. So then what had to go wrong here, tracing back through, it's that initial assumption, right? Our initial assumption is that suppose this is the case, that it's never 0. Thus, it has to be 0 somewhere. Thus, there exists some z0 such that P of z0 is equal to 0. And that's it. We're done. Okay. Now, how is this related to maybe other versions of this fundamental theorem that you've seen before? So note, if P of z is that polynomial, right? So a0 plus a1z plus all the way up to a sub n z to the n. N is greater than or equal to 1. A sub n is not 0. Then this fundamental theorem guarantees this has at least one root. Say z sub 1, right, is my first root. So say z sub 1 is my root guaranteed by fundamental theorem of algebra. Okay. Well, then I can factor this. So I won't go through the justification of this. This might maybe show up as an exercise, or maybe show up as a problem on your next midterm or something. Then we can show that we can write that P of z is z minus this z sub 1 times, say, q sub 1 of z, where q sub 1 of z is a polynomial of degree n minus 1. So if we start out with a polynomial of degree n, we are guaranteed a root. If n is greater than or equal to 1, we're guaranteed a root by fundamental theorem of algebra. We can actually rewrite this polynomial as z minus z sub 1 times q sub 1, where q sub 1 is a polynomial of degree n minus 1. If this is greater than or equal to 1, we can keep going here, right? So if z sub 2 is a root of q sub 1 of z, note we are guaranteed that such a root exists so long as n sub 1 here is greater than or equal to 1, right, then we can rewrite this further as P of z is z minus z sub 1 times z minus z sub 2 times q sub 2 of z, where q sub 2 of z is a polynomial of degree n minus 2. We can keep this process going, of course, until this n minus k becomes 0. Okay, so continuing on, what does this mean? So P of z is equal to z minus z sub 1 times z minus z sub 2 times z minus z sub 3, and so on, times z minus z sub n, okay, where the z sub i's need not be distinct. Some of those may be the same, right? You know this is a possibility. When that happens, right, after you have efficiently collected all terms in a factorization like this, the exponent on that linear factor for that associated root is called the multiplicity of the root. Okay, so we call that the multiplicity. Okay, and so this is where we introduce the terminology counting with multiplicity, which you've heard for algebraic roots before. So where the z sub i's need not be distinct. And so what does this mean? It means that it can't have more than n distinct zeros. It can have, though, up to, it can have n distinct zeros, but no more than that. And typically, maybe there's going to be some repetitions here. The main thing is that complex polynomials fully factor. Okay. If you want to make a very nice statement here, you could say that counting with multiplicity, every complex polynomial has exactly n roots. Counting with multiplicity would say if you have a double root, it gets counted twice. If you have a root with multiplicity 3, it gets counted 3 times. So even though it is the same number, you're counting it 3 times. And so you've seen this in the context, if you ever had a differential equations course, right? This came up in when you were in various ways when you were, say, for instance, dealing with the characteristic polynomial, right? So if you knew the characteristic polynomial for some differential equation, then there were cases of what the form of a general solution to the associated homogeneous equation could take, depending on the multiplicity of, say, a root of the characteristic polynomial, right? Okay. So there's another nice fact. We have a couple more named things that follow here. So one's the maximum modulus principle. I'm not going to fully prove it. I'm actually not going to prove either. There's an associated lemma in the textbook, and I'm not going to prove the lemma, nor am I going to trace through the proof of the theorem either. But I wanted to at least state it because it's nice. Okay, and so let me go ahead and state one more theorem. So I will state one more named theorem without proof. The proof is not too difficult. It is just a little tedious, and so I will I will avoid it for now. I might, if I have time later, go back to it. Otherwise, I will relegate it to supplemental material. So this theorem is the following. So this is the maximum modulus principle. So this is a direct result of all of these things that we've been proving. Okay. So if f is analytic and not constant, so if f is analytic and not constant in a given domain D, then the modulus of f of z has no maximum value on D. i.e., that is, there is no point z0 in D such that f of the modulus of f of z is less than or equal to the modulus of f of z0 for all z in D. Okay. What is the idea? So let's just do the idea of the proof. We argue by contradiction, so we assume that the modulus of f does have a max value. Then we will show that such an f with these assumptions must be constant. Which will contradict the fact that we've said that it's not constant. So this is the idea. Okay. This relies, so this approach relies on the following lemma. Okay, so this relies on a lemma. Okay, which is independently of some interest. So what does the lemma say? So suppose that we do have a maximum for a modulus. So suppose that the modulus of f of z is less than or equal to the modulus of f of z naught at each, for all z in some neighborhood. That is, modulus of z minus z naught is strictly less than epsilon, in which f is also analytic. Then f of z is constant. Actually, it's constant value f of z naught throughout that neighborhood. So this is where the lemma comes in. Okay. So suppose it has a maximum value. We have this lemma. This lemma comes from the Cauchy integral formula. I'm not going to go over the proof of the lemma. So proof is a Cauchy integral formula. It's not a. There is a little bit of work here, but not too much. It falls out of the Cauchy integral formula if you're careful. Okay. This passes through something called the Gauss's mean value theorem, which is basically you look at Cauchy integral formula and you do a change of variables into polar coordinates, and you get something that is sometimes called the mean value theorem or the Gaussian mean value theorem. But this is what it is that's going on. Okay. Now, what is an application, say, of the maximum modulus principle? So, thus, how does this, say, relate to what we know about things? Right? Like, how does this relate to what we know about when functions are guaranteed to have, say, maxes on some set? So, note that here, maybe something you might consider subtle is that we're on a domain D, which is open necessarily, right? So the reason why this is very important is because we know that we already have a theorem that if you have a continuous function, right, which is a lower ordered thing than analytic, on a closed and bounded set, then you're guaranteed maximum values by this max-min theorem. Okay, and so it's very important that this is on a domain D. Okay, this maximum modulus principle is going to be very, very false on a closed and bounded set. Okay, and so to see an application of this to parts of a closed and bounded set that are open, say its interior, right? This is going to show, or it's going to shed some light on where the max or the min has to happen, right? So here we're going to talk about all this in terms of max. We don't care about min because that we can talk about mins, we can view them as minus maxes, right? So we don't care. Everything's a max to us. So what this says is this allows us to, say, pinpoint exactly where maxes have to occur, right? It can't occur on the interior because of the maximum modulus principle, so they have to occur on, say, the boundary, right? If we're in our usual nice case, so we had some boundary curve bounding a closed bounded region in the plane. Okay, and so if f is analytic on the interior of a closed and bounded set. So if it's analytic on the interior of a closed and bounded set, say R, okay, then it's also continuous throughout R. So if it's analytic at each point in the interior, then it's also continuous on R. But it's continuous on a closed and bounded region R. This means, right, that fz has a max value somewhere in R, okay, i.e. there exists m such that modulus of f of z is less than or equal to m for all z in R, and equality happens at least one point. Okay. Now, if f is constant on R, well then f of z is just equal to m for all z, right? And we're done. But if f is not constant, Well, we have an analytic function on the interior of R. That's a domain. And it's not constant. By the maximum modulus principle, the modulus of f cannot have a maximum value on this domain, which is the interior of R. F cannot have a max on the interior of R. So what did we just show? It has to have a max value on R, but it cannot have a max value on the interior of R. So what did we just show? Well, if f is continuous on a closed boundary region R, and is analytic and not constant on the interior of R, then the maximum value of the modulus of f, okay, is, or I should say, always occurs on the boundary of R and never in the interior of R. Okay. And this max value is attained by the same max-min theorem from before. Okay. All right. So this is a nice fact, okay, that might bring you back to some conceptual questions in Calc 3 when you were originally, like right before you started, like your Lagrange multiplier talk in Calc 3. The questions of where maxes or mins could occur, right? In Calc 3, you were allowed that they occur at critical points in the interior or somewhere on the boundary, right? So there were conditions you could impose, right? Like the function had no critical points in the interior, then it had to, a max or min had to happen, say on the boundary. So this maximum modulus principle is a nice way to get a lot of info on how this modulus of f can behave, how it's allowed to behave. The most important thing to note here, though, is that this is true on domain D. So the openness of D is very important here, so don't let that fact slip by you. Okay. So anyway, I think that's all for today. So I'll start with a discussion of sequences of series again tomorrow, which is going to mirror very closely how it worked in Calc 2. And after we've kind of gone through some basics, we will show Taylor's theorem, which is finally going to give us, so you already know Taylor's theorem from Calc 2. We're going to have complex Taylor's theorem, which is going to immediately pop out. Like the statement of Taylor's theorem is going to include this fact that this word we've been using, analytic, means exactly what it meant for real valued functions in the sense that it gives us a power series expansion. So we're going to have a power series expansion, and then we will have finally, caught up to me spoiling everything earlier, and telling you basically all of these facts in like the first week of class. We will have finally shown all of this stuff. So today I'm going to have office hours here in a couple hours, so from 2 to 3. So come by if you have questions about the homework. I'll post your next homework either tonight or tomorrow, and it will kind of tidy up some of the stuff you've been doing, and also have you doing some stuff involving power series. So anyway, that's the